So good morning, everyone. Thanks for coming. And I am part of NVIDIA. Some of you might know our organization. I'm here to talk about, in general, some of the fundamentals of how the computing has evolved and how does GPU come into the picture. And later on, the CDAC team will be helping you out with respect to the hands-on part of it. But hopefully this session will be a session for you to understand the reason, rather the why part of it, rather than the how or what part of it, which the CDAC team is going to cover into a lot of details. So I wanted to take you through a journey of how the computing world evolved. I think in the earlier days, it was said that the domain scientists concentrate on the domain part of it, but then over time, it has obviously changed. Without high performance computing, it is impossible to do science. So the domain scientists also started looking into the architecture of high performance computing so that they can do larger workload simulations or do things faster, so that maybe more ensembles can be created, and there may be various reasons for it, right? So, but I wanted to take you through the evolution. For example, when the initial era started, there were computers having more of a sequential mindset. In fact, I keep on debating this in many of the organizations also, like, why do we still teach sequential programming in computer science? All the algorithms, whether it is sorting or any sort of other algorithms, when we start teaching them, we teach them with a sequential mindset on how those for loops are, which means to do one activity at a particular time. But as you know, the real world itself is parallel. Our mind thinks parallel, even our computers think parallel, right? So is it fair to even think sequential? And that's where a lot of things kept on changing. So it started with the sequential world where there is one CPU and there's one action which happens, and the CPU is connected to a memory. So it will work on the data which is stored in that particular memory. Generally, you will refer it to as RAM memory. So this was good. It solved certain amount of problems. Maybe at that time, the maximum performance it could give was in megaflops. Some of you, I hope all of you understand this definition of flop, which is floating point operations per second. So every CPU is measured based on how many operations it can do per seconds. And that's how you calculate this, right? And there are different kinds of operations. I'm not going into that debate, like 64-bit, 32-bit. Nowadays, there are 8-bit computing. Algorithms have been developed to even work on 8 bits. So it's an algorithmic based optimization, not just hardware based optimizations, where a lot of changes are happening in this space as well. AI is one example of it, where you're going to look at today. AI mostly works on 16-bit and 8-bit precision. It doesn't require 64-bit precision. It is very good at working at those lower precision numbers and still do a good job on it, right? Because it has a way to backpropagate some of these ways. So started with sequential world, but then we hit the roadblock. We could not become any better. Then you move towards multi-core era, where instead of one core, you got multiple cores. Nowadays, even your phones doesn't have a single core. It has multiple cores. So obviously, the supercomputing work that we all do should have multiple cores. But it's not about the hardware being changing. What I'm trying to tell you is the change in the software world. When the hardware changes, the software world changes. Everybody had to now start thinking on how to utilize this multiple cores using programming models or methods like OpenMP or pthreads, right? So you had to explicitly write in your code that I want to divide this loop or this work across multiple cores. Just writing a sequential code will not utilize all the cores. You will end up utilizing only one core of that whole machine and basically wasting a lot of time or the resources which have been practically given to you. And then within the node, all good. But then that also, it maybe you went from megaflop era to gigaflop era, which means you are able to do much more work in one single machine. but one single machine has its own problems. And that's when the distributed era came into the picture, which is multiple machines were connected to each other with a very high speed, high bandwidth, low latency network. It is not the network that you traditionally see here, which is this Ethernet based network. It is a very specialized network, for example, InfiniBand, which gives you 200, 400, 800 gigabits per second kind of a speed, and the latency is also very low. So it's a different specialized network with different network topology, which were designed so that these computers can talk to each other and share data with each other. So hardware evolved, but then again the software had to evolve. Now all the domain scientists had to now change their code from sequential program to multi-core program and now to distributed programming era, which means now you had to think in terms of distributing your data across multiple nodes, and you had to take care of the aspects of how well you can distribute this data or communicate, because in the end, as you know, the Amdahl's law, you will be bottlenecked by the smallest thing in the slowest part of your overall system, which means even if your computer is very fast and if your network is very slow, when you communicate, you will be bottlenecked by that network. It doesn't matter how nice computer that I give you, but if the communication is slow, you will be bottlenecked by that communication. So there were a lot of evolving aspects, algorithmic changes which happened in the domain side also to incorporate the distributed programming approach. So we went from megaflops to gigaflops to teraflops. Now we are in petaflops and exaflop. We are talking about exaflop kind of a system nowadays. Not even tera is something that you get now in your one single system. So this was all good. Then came an era of something called as GPUs, and GPUs were generally referred to as, I don't know if any of one of you here is a gamer. Is anyone a gamer here? At least a few, so you might know what the gaming engine there is. The core is GPUs. The name stands for graphics processing unit, right? So it was meant for doing graphics. But if you look, what is graphics? Graphics is, if you have a 1024 by 1024 resolution picture, what you're trying to do is you're trying to paint those pixels in red, green, and blue. And every pixel to a large extent is independent of each other. So if you see, it is actually a parallel computing workload, right? So the first workload of parallel computing where GPU took over that workload away from CPU. Earlier, this was done on the CPU. So this is what we call as offloading and giving it to some other processor, which is very good at doing something. Like GPUs were very good at doing graphics. So the graphics was taken away from CPU and the graphics was rendered in the GPU, while CPU used to run your other task so that it can run other algorithms and everything, run the operating system, for example, and the graphics was taken care by the GPU. But GPU inherently was designed to solve this problem of parallel computing, which was the reason why GPU also became really popular for other workloads from graphics. Then some of the researchers like you, they went ahead and started using the graphics pipeline to do other kinds of work. For example, for doing CFD workload, for working on Fourier transforms and so on and so forth. So they were writing graphics kernels or graphics pipeline utilizing to work on GPUs. Later on, this was realized and we evolved to do something more with that, and we created a new programming paradigm called as CUDA. And I will talk about that in a bit, which kind of helps you to write really efficient codes on the hardware, which is NVIDIA GPUs. And I will talk about the architecture in a bit. By the way, if you have any questions, please feel free to raise your hand and ask your questions. We don't need to wait till the end. If there's any doubt in any of the terminology that I'm using, just let me know. Yeah, I will be more than happy to answer that for you. My goal is to explain to you why we are here and why we are talking about it. The GPUs have evolved to a large bit now, so I'm not going to cover those into a lot of details, but the boundary between CPU and GPU is kind of reducing as an architecture to some extent. Nowadays, we have newer generations of GPUs. So you're going to see in the coding, we are going to tell you CPU has a different memory, GPU has a different memory, you need to copy the data and so on and so forth. But if you look at how things have evolved, on the left hand side, what you see is a CPU of ARM architecture by NVIDIA called as Grace. And on the right, and then you have the Hopper architecture, which is the GPU there. And if you see, CPU and GPU are actually having a coherent memory. These kinds of architectures are called as memory coherent architectures, which means both of them share the same memory. So what happens in that case is you don't have to do additional work to primarily do things like transfer the data, so on and so forth. If it's a parallel computing job, you give it to GPU. If it is more of a multitasking job, CPU runs it really well. So the newer architectures are becoming way better in terms of programming. And the advantage of this is also the fact that now you can store more data into one system rather having to keep on transferring data back and forth. So we are not, the reason I am showing this slide is not to confuse you, but to tell you that whatever you learn today is just the surface. There's a lot which has evolved as an architecture, as a programming model, and things have become much simpler. Okay. So as I said, the GPU system over time has evolved, and we don't talk about just multi-cores. These multi-cores are combined together to become a full-fledged GPU. Then you have systems now, each system can have 8 to even 16 GPUs inside. And then as our CEO also says, the new GPU is actually the whole system itself, which is the whole cluster. So you can write code in a way that the code runs across the whole cluster or hundreds of thousands of GPUs in a much more efficient way. And there are various libraries, frameworks which can help you to do that. Single GPU can help you to some extent, but the newer programming model is what you're also going to learn is how to distribute your work across thousands of hundreds of GPUs as well, is what is the paradigm right now that we are talking about. So let me skip this slide. I will try to cover the fundamentals of the processor itself. So if some of you would have taken some courses maybe on the computer side of the world, generally any processor, whether it is CPU or any kind of a processor that goes in your mobile, which is ARM or Intel processor, any other processor, basically has three components in that processor. One is ALU, which is arithmetic and logic unit, which is your actual core, where you do addition, subtraction, multiplication, all these operations. Then you have the control logic, which kind of defines like which instruction you're going to run, like is it this instruction or that instruction. And then you have your cache. Cache kind of stores the data that you have. So you bring your data from RAM to your cache so that the ALU can actually execute it, right? So these are the primary components in any processor. It doesn't matter which kind of a processor it is, whether it is your CPU in your mobile phone or whether it is in GPU or anything. Every processor will always have these three components. The distinction, what happens is generally, can anybody tell me how many cores nowadays you get in your CPUs? 16 cores. Any further? You can even get 128 cores nowadays, right? Obviously with hyperthreading and all, but you can get up to 128 cores also. Okay, so CPUs, they do provide so many cores, but you can think of like every processor has a real estate of silicon, right? So your chip comes like this. It's like a real estate of silicon, and you can put transistors on it, and you have to decide like what the transistor will do. Will it do ALU? Will it do control? Will it do cache? Because it's at the end, it needs to be in that form, right? So in the CPU side of the world, you will get lesser number of cores in few hundreds. The control logic is very high. So they need to do a lot of multitasking control kind of operation. Can anybody give an example? Right now I'm running my laptop. It is running on CPU and operating system. Right now my Microsoft presentation is going on. Along with that, Slack is running, Outlook is running. In between it has to switch, right? My CPU has to switch. It is doing a lot of control operations. So it has to do all of that multitasking kind of a job. So it puts a lot of effort towards this control part of the world. And then cache. It does provide a lot of cache. And I'll tell the reason why it requires a lot of cache. But when GPUs were born, they use that real estate for some other purpose. They said that we will give a lot of importance to parallel programming. That's why we'll give you a lot of cores. Okay. So the GPUs don't have hundreds of cores, but they have thousands of cores. They don't have hundreds, but thousands of cores, and you can launch 10,000s of threads on GPUs. Okay, so they are fundamentally a parallel programming supercomputer, if you were to say. That is how the design was made. Generally the parallel programming is, if you see, one of the examples is for loop. If you are doing vector addition, very simple example, what you're doing is for loop adding two vectors. So every data is doing one operation. What is that operation? Addition, right? So there is no control which is required. What you want to do is addition operation on lots and lots of data in parallel, primarily. This is just an example of the most fundamental example of a parallel computing paradigm. So do we need a lot of control logic? No. So we gave lesser importance to the control part, and obviously the cache was also lower, and we'll talk about that in a bit. So if you see, the main difference is nothing but on how the CPUs and GPUs use their silicon real estate or where the transistors are put. And this is a cartoonish figure, but it kind of tells what is the difference between CPU and GPU. Anybody would like to look at this and tell me what those blue, green, and other boxes are? What are blue and green boxes? Cores, right? So your CPU has certain amount of cores which are lesser number, while GPUs are lot more larger number of cores. But do you also see the size difference, right? So the GPU cores are much more smaller, or in simple words, I'm just telling it, but they're much more simpler. They can do fundamental things, like I said, vector addition or things like this, one thing at a time, not like CPU cores, which has a lot of control logic inside them. So we reduce that part quite a bit. But you can have thousands of them, and I will come to that part. What do you think is that gray area? Cache. It has a lot of cache, obviously. GPUs also have cache, but it is limited in number, and I will come to that part. So just to talk about, by the way, in no way I am saying that one architecture is better than the other. Okay. What I am saying is every architecture has its strength and every architecture has its weakness. What we have to do is we have to take the strengths of both architecture and use them together so that your code can run really well. Your codes will generally have two parts. One part which needs to run in parallel, and the other part which is still sequential in nature, or which requires this multitasking kind of a job, which can still run on the CPU. So one advantage of CPUs, this is slightly old version. As I said, the newer generation of memory coherent architecture may not have some of these things as true, but I am still referring to the slightly older versions, which some of the organizations have, like Volta cards or Ampere cards and all. So one of the biggest advantage of CPU is that CPUs have lot of memory. Can anybody guess, like, what's the maximum memory you can have in a CPU computer, as in your machine? How much data can you allocate? I know astrophysics data and all this data is pretty large, right? Terabytes, right? We are talking about terabytes. What could be the theoretical number? It's a 64-bit operating system. 2 raised to 64, right? Because 64-bit, you can only go from 0 till certain number, right? So that's what is the 64-bit operating system says. So you can have some terabytes of memory. Every core runs at a very high clock speed. So if you look how the processes run is, they have a frequency attached to them. They run at few gigahertz. The higher the gigahertz, the faster the clock speed, the faster your CPU can do a job. So the CPU cores can run at a very higher clock speeds. They have a much more higher frequency at which they can run, so they can execute very fast. If you give them any instruction, they can execute it very fast. They have a very higher clock speed. And they have caches. Now they have a very high speed. They can run instructions very fast. Now, can anybody relate to why caches are given? I can execute, but what do I need to execute? Data. Where does the data sit? In the cache. So can the data sit in file system? You generally have files, right? Files and all, JPEG, this file, that file system. File system is very slow, right? It can read at few megabytes per second or whatever something. And then higher than that, the speed is of RAM. When you do allocation in, then it goes to RAM. But even RAM is slower. You need the data which is more frequent to be brought into caches, because I can only execute it if I have the data. If the data is sitting very far from me, then I cannot execute it, no matter what big system I provide you, better CPU I provide you. But if your data is not in good shape, then you are not going to utilize the CPU. You might be utilizing it 20-30% only. So many times we blame the architecture, but actually the problem lies in the data structure that you use. If you change your data structure, you might see 2 times, 3 times speed up even without writing any parallel codes, for example. So that knowing of that data structure is very much required. And CPUs can run few number of threads, maybe around hundreds of threads very quickly. There are some weaknesses of CPUs. For example, their bandwidth is very low. If you don't write good data structure on the CPU, the cache misses are very costly. So you'll end up basically wasting a lot of time waiting for the data to come to the CPU. And yes, they are low performance for what, but I will come to that in a bit. Any questions so far on this? Did you understand the concept of cache or speed and all? Now coming to the GPU, obviously GPU has certain advantages. First of all, GPU's memory is very fast. It uses a specialized memory. It provides you much more higher bandwidth in terms of reading and writing onto the RAM. So its memory is different from the CPU, and it can basically read and write at a much more faster rate. Obviously, the reason you are so many cores. If you don't read or write at that speed, then there is no use of having so many cores, right? It has more number of cores, simplified cores, but you have more number of cores. And I'll talk about that latency tolerant maybe in a bit if time permits. These are called as high throughput architectures. The disadvantage of the older generations of GPU is that if we give you more higher memory bandwidth, I cannot give you a lot, which means if I'm giving you higher speed of read and write, I cannot give you terabytes of memory. It will be in giga. It will not be in tera. So the GPUs have limited RAM that you can have or fit your data in. So that's why I was telling that we'll have to keep on pushing the data to the GPU, bringing it back, pushing to the GPU, bringing it back. And this may become your bottleneck in case it's not done in a very efficient manner. Okay. This has been solved by the latest generation. You don't have to worry with the memory current, but I'm referring to how the programming has also been done. Okay. And if you write a sequential code on GPU, or if you write a code where only you need to do operation on 100 elements, GPU is going to be much slower than CPU. It is meant for doing massively parallel operations. If not 10,000s, few 20,000, 40,000 threads, or millions of threads, elements you can work in parallel. It is supposed to be used for that kind of a workloads and not for doing simple things. For example, adding 100 elements or things like this. It will be much more slower. It's like using a hammer to kill a fly, right? You won't do that. So it's meant for massively parallel. So if you write codes which are sequential in nature or which doesn't require thousands of cores, then your code is actually going to be slower than CPU. You're not supposed to use GPU for that purpose. Okay? Is it clear? Okay, so no matter what how should I say? For example, your files, whenever you read or write, like let's take example of network. You can send data or receive data at some speeds, right? Megabytes per second or something. Similarly, your file system, which is the lowest most, which is your disk, actual disk, can read at certain speed, megabytes or gigabytes per second, something. The speed is defined based on your file system type and all. Above that is your RAM, right? Random access memory. It can read or write at a faster speed than file system. That's why it is limited in number. If you see, it is actually a shape like this. So always the memories are like this. Well, first you will have your file system, which is much more larger in number. So it's like this. So the higher you go, the better the speed is to read or write, right? And the lower you go, the more you get, which means the size is better. So then you have your file system, then you will have your RAM. So whenever you do, if you have written C codes, malloc, or whenever you write program, basically all that memory goes to RAM. Then you have cache systems in every CPU. You have L3 cache, L2 cache, L1 cache, and then you have something called as registers. So what happens is whenever you do, suppose A equal to B plus C operation, inside the system, what happens is it will have instructions, lower level instructions based on CPU, like load B into register 1. Then it will have internally code like load C into register 2. Then it will have add R1 comma R2 and then store in R3. That's how all the operations actually happen behind the scene on your computer when you write. So your compiler actually converts whatever code you write into these kinds of instructions on your CPU, right? So what I'm trying to say is whenever you do anything, the data will always go like this. Always will traverse like this before the CPU can actually, the ALU can actually execute it. Does it clear? So what I'm saying is this RAM of the GPU has higher speed as compared to what you get in your traditional CPUs, which is DDR. Generally the word DDR and all you would have heard, while GPU RAMs are very different as compared to what the CPU RAMs are. Okay. Any more questions? So if I were to say in very simple terms, the fundamental difference between a CPU and GPU is this. Okay, so if I were to go from here to airport, and if I were to take one of you with me, I'll choose a bike. It's much more faster, right? It can run and it can take one of you or maybe few of you. I don't want to do triple sitting here. So that's what it is. But what if I want to take all 50 of you together? Then I will choose a bus. Bus is slower than a bike, right? But it can have 50 seats and all 50 of you can go together. So rather than doing back and forth, back and forth, back and forth to make all 50 of you reach there, I would choose a bus, right? So GPU is more of throughput based architecture, which means if you want to do operations which are the same operation and you want to do a lot of them, the GPUs are very good at that, right? While the CPUs are very good at doing multitasking like running operating systems or doing few tasks very fast. Okay, so CPUs are having a lot of control logic. If you have a lot of if and else statements in your code, it's like control jumps, right? If here, then do this, if that, then do that, if this, then do this. This is not very good in GPU world. If those kinds of programs are not very good because it's not very good at jumping from here to there. It is very good at doing same thing like graphics. I gave you an example of graphics, right? So that's what GPUs, the difference between latency and throughput is. CPUs are referred to latency based architectures while GPUs are referred to as throughput based architectures. Okay, is it clear? And the good part is that this architecture is applicable to almost all the fields. It doesn't matter what it is. There's this law, which is a principle, which is called as 80-20 principle, which means 80%, it's general word, like 80% of the bugs come from 20% of the code. Similarly, 80% of the time of your application is spent in 20% of your code. And mostly it's those for loops, the work that you keep on repeating again and again, right? And that is the part that you need to send to the GPU. The rest all still runs on the CPU as it is, right? And whether it is genomics, whether it is astronomy, whether it is astrophysics, whether it is AI, all of them have fundamentally parallel computing nature behind the scene. Many of them, in fact, can be boiled down to very simple operations like matrix multiplication. And GPUs are very good at doing matrix multiplication because it's fundamentally a parallel operation, right? Larger the data, the larger the matrix is, the better GPU will do. That's how it is. Okay, any questions? So NVIDIA obviously was started this revolution. So we do have a lot of SDKs and all. I'm not going to cover this part because this will be covered in the hands-on part. But what I wanted to let you know is many of you might not even end up writing parallel codes because over time the ecosystem has been developed. Most of the members in the domain science will end up using some libraries. So libraries are already written you on GPUs and you can directly use them. One of the biggest example of it is AI, for example. In AI world, whether it is convolution neural network or LLMs or whatever it is, all of them behind the scene, whether it is PyTorch, TensorFlow, doesn't matter. Behind the scene, it will use an NVIDIA library, which NVIDIA has developed, which does all of these operations for you so that you don't have to reinvent the wheel quite a bit. Whether it is fast Fourier transforms, whether it is matrix multiplication, any of these tasks, there are already libraries there. So rather than reinventing the wheel, first explore if you can use those libraries. If not, then what you see is from left to right are different approaches to writing programs on the GPUs. The most left-hand side is what the language is understood. One great thing about Java when it was born was that Java introduced many of the concepts as part of programming language itself. And that's why it became really popular in the enterprise side of the world. It made asynchronous programming, multi-threading. Threads were part of the language itself. It was not an operating system concept. It was part of the language itself because it understood that things are parallel and it should be part of the language. C and some other languages like Fortran and all, they took a long time to understand this fact. It took them, but it's better to be late than not to have it. So the latest standard of C, like C++ 11, 17 or Fortran 2018, now part of the language itself, they have concept of parallelism inside them. Like there's something called as STL or features, which is standard template library, and it has std_par as C++ feature where you can create threads, and it is part of the language itself. So every compiler has to support it. So once it becomes part of the language, it has a mass adoption, right? So that's the good thing about it. So Fortran 2018 also have something called a do concurrent, not just do, but do concurrent. So that's the good part of it. So if you were to start in this field, maybe using this language is better because once it's part of the language, it gives you also freedom or independence or portability from different hardware vendors. Right? So you can run this code on CPU, you can run, if you don't have a GPU, if you have GPU, you can run it on GPU, so on and so forth. So if you're looking at those kinds of things, standard languages are a good choice. They started some time back, it was not so much stable, but now the ecosystem has become better. Domain scientists generally don't prefer to write lower level codes. So there are other approaches, for example, directive based programming. Has any of you written any directive based programming like OpenMP or anything? So directive-based programming, as the name says, is giving direction to the compiler. You don't write parallel code. You just tell to the compiler, like here, It is telling that make that particular part of the code parallel. You see hash pragma in the between, hash pragma. So it is telling compiler, this part of the code should run in parallel. For example, a for loop should run in parallel, and you're just giving a hint to the compiler. Compiler, please make this parallel for me. And the compiler behind the scene goes and writes a CUDA code or parallel code for you. So that's the beauty about the latest generation of compilers. They are very good at doing it. The only thing is you are telling it what to make parallel. There's nothing called as automatic parallelization. Still, we have not reached there yet. You have to still tell it what to make parallel. Last but not the least, some of the things that you're going to study today is the aspect of actually controlling every bit and piece of how your program runs. Like how many threads I should launch, which thread accesses what data. That's like for the ninja programmers on the right hand side, where you can control every aspect of your hardware and software and algorithm and get the best performance out of it. Many domain scientists also prefer that. What I'm trying to tell you is there are different approaches to GPUs. You choose your approach based on your convenience and your needs. If you need portability, maybe the right hand side may not be a good approach for you because it is very specific to NVIDIA hardware, for example. If you want portability, but slightly more control, then directive based is the best approach for you because you are still directing it, right? What to do. Standard language is part of language. It needs to be abstract. It needs to be working for all the hardware. That's why you may not get the best performance. So what you are seeing as this is you get the best performance when you control everything. The more abstraction I give, the lesser the performance can get. So it is your decision whether you want to use the abstraction or you want to control the performance of your software. Okay. And you can mix match. For example, you can have one part in standard language, another part in directive, and one part in CUDA, specifically the right hand side. So you can mix and match also between them. That's also a valid approach. For example, if one of the kernel is taking majority of the time, you take control of it and optimize it to the max. Rest all you keep it with the higher level thing. Okay. Is it clear? Any questions so far?
Questions for discussion?
Either I am too good or you're all already sleepy.
Anything you want to make your code faster?
Hi, Rahul here. So I had a question. So if you have more number of operations going on in GPU, maybe it's simpler operations, the data flow rate should be higher from file structure to the RAM. So where is that and how is that taken into account?
So I am not covering the file part of it. File to RAM is not a GPU problem, right? File to RAM is more of a fundamental problem of the file system itself, and it can be solved in other ways. So you have parallel file system nowadays. So you can actually store data and read very fast from the file system to the RAM. So it's solved in a different way. It's not solved by the GPU. It is solved in a different way, using concepts like network file system, parallel file system. So whenever these clusters or cloud systems are made, all this goes as part of the configuration. Like at what speed I would like ideally to read or write to my file system. At that level, that's how you decide the configuration of this high performance computing system. So GPUs come into the picture once the data is in GPU RAM, right?
Nice talk. And there is one question, this C photon CUDA, previous slide, I think, whatever, yeah. Are they standard C photon or you have a NVIDIA version of them?
Which one are you referring to? The left
When you
hand
mix
side?
these, like, oh, yeah.
So what you see on the most left hand side, like C and Photon standard committee defines the standard. right? Like how the API should look like and all. Then there are different compilers who implement that standard, like GCC or Gfortran is the open source compilers who implement that compiler, the standard, right? So that's how all the compilers work, right? Or how the standards work. So there is a committee which defines the standard and then all the compilers implement it. So we have a NVIDIA compiler who adheres to that standard, which is called as NVIDIA. This slide which I skipped is where it has. So it has a C compiler, it has a C++ compiler, it has a Fortran compiler. So it's like NVC++ on the left hand side is the C++ compiler, NV Fortran is a Fortran compiler, NVCC is the C compiler. Like that, you have different compilers. You also have different libraries. As I told you, BLAS is for linear algebra operation. For tensor operations, you have tensor. For solvers, you have different CFD solvers. So you have a one for solvers, you have for sparse operation, you have sparse random number generators, fast Fourier transform. There are hundreds of libraries also which gets packaged as part of NVIDIA HPC SDK. And all these compilers support all those programming models that I referred to, which is standard C++ and Fortran, or OpenACC is also a standard. It's a committee which defined the standard and then compilers implement those standards. So we do support those OpenACC and OpenMP, and then CUDA indirectly, what you see there, so what you see on the extreme right hand side is an example of a C code, which you're going to see. The right hand side code that you see is a C code actually, right? If you see int main, malloc and all, it's a C code. The only thing is we have appended with some additional keywords like global, thread ID and things like this to launch. So it's not part of the standard, but it is extension to the standard which will make it run on NVIDIA GPUs. So that's why I said the right hand side is very specific to NVIDIA GPUs. So you are controlling a lot of aspects of how your program runs. While the other two are standards by the language, by the committee, and all the compilers support it. And NVIDIA has its own implementation, which will run the best on NVIDIA GPUs. Does it answer?
GPU to another, they are taken care of.
They take care of. That's one aspect of it, which is one thing about NVIDIA GPUs, which I'm not showing is your same code when it goes from say Ampere to Hopper or something. If you just recompile the code, you will see a better performance already. The only caveat there is that your code should be able to scale, right? If it is not utilizing the previous generation hardware, then it cannot even utilize the newer generation. So because it's becoming faster and faster, right? You just have to recompile the code just to answer.
Hello. Yeah. So I want to use a Python wrapper for this GPU. So which wrapper you prefer, and will
there are different. So Python yet have not come out with it's not officially part of the standard yet, but there are different implementations on Python. There is something called as CuPy. There is something called as PyCUDA. Then there are various methods out there, and NVIDIA also has its NumPy library equivalent, cuNumeric. It's called as cuNumeric, and it is basically like Numba or something, and you can just replace it with cuNumeric and it will work. So because Python yet doesn't have a standard for these kinds of things, the open source people have come together and developed these implementations on Python. So we do have cuNumeric from our side, cuPyNumeric, which is the Python wrapper for doing all of this activity. But open source is also good. You have PyCUDA and all, Numba and all. That's also okay. How many of you use Python here? And how many of you use C? Fortran? It's good to see, as in last time when we did the session, there were a lot of C and Fortran, like when we started our journey. Today, everybody has jumped to Python. It's good. So Python, we do have something called as CuPy numeric. It doesn't matter. What I'm teaching you is the fundamental. The same concept will apply in Python. The same concept will apply in CUDA. So what I showed you here in terms of those pragmas, in case of Python, you will have annotations there. That's it. That will be the change. It's just the language change. But the concept will remain the same. You might find it difficult for the hands-on session. Most of them are Python developers.
So if language isn't an issue, then I mean, writing codes in Python is a lot easier than writing codes in C if you have complex instructions to be followed. So what's the bottle? So as per your, as per my understanding here, GPU, the language is not an issue. So you can code in any of the languages. Is that correct?
So let me give you how this higher language. So I don't want to go into a debate of language, right? Like which language is better than the other. But let me tell you the fundamental of what can be an issue, right? Why sometimes people still write lower level. For example, Python and all, if you write annotations and all, what happens behind the scene is, what behind the scene those frameworks will do is they will convert it into a C code and then compile it behind the scene. Okay? Or some of them will directly write assembly level code. But there is something called a JIT compilation, just in time compilation, which happens. So if the framework is really good, it can give you the performance, but not always. Like for example, PyCUDA and all, they give you an option, you can stay at Python level, but you can also write a kernel like this, GPU kernel, and give it as a string to compile. So rest all code is Python, but only the GPU part can be given as a string so that it can compile it, keep it ready, and you directly give it the Python data directly. So it depends on what your necessity is. Some of the frameworks do a very good job in that JIT compilation. Some of them don't. So if you want to still get best performance, people may move to, in the Python world itself, give these kinds of C codes inside. Does it answer?
Sorry, somebody had a.
So as you said, the GPUs don't have a lot of cache, right?
It does
Yeah.
have cache. It's used for a different purpose, but yeah, go ahead.
So what are the limitations? So basically, the way you talked about control and all these things in CPU. So the way we write code, how does that translate to a GPU code? For example, when we assign memory to integers and float and all these things, in a GPU, because it doesn't have like the same amount of control and cache the way CPU does.
So don't
So how
worry
does it
about,
change?
nobody writes code keeping into account the size of cache. You ever write a code? No, right? The only thing that you take care of is that it can fit in the RAM, right? So suppose if my GPU has 40 GB memory, if I can fit in that 40 GB, really great. If I have suppose 60 GB, right? Then I will have to do some additional work of keeping some data in the CPU because it has larger memory, transferring first 40, work on that 40, bring back that 40 and then transfer the rest 20. Are you getting it? So you don't work based on cache. You never write code based on, oh, I have 20 MB cache, so I should write it like this. Never. You never write code based on cache. On some people do who are ninja programmers, but I don't think so. We need to do that here. The only thing you have to take care of is as much as memory that you can allocate. If it's a 40 GB GPU, then you can maximum fit 40 GB into GPU. After that, it will be out of memory, right? And if it doesn't fit, then obviously. But I don't believe that has been a problem. The problem is, can you actually utilize the whole GPU with that 40 GB? Maybe 20 GB is enough to fully utilize the GPU. The amount of computation you give is also important, right? So what you can do is, generally it's called as pipeline based architecture, which is you transfer 20 GB, start working on the 20 GB, the computation, and in parallel transfer the rest 20. It's called as pipeline based architectures, right? So based on your code, it will define like how much data you want to actually allocate. It's not based on just, we have never seen in many, unless you are in fields like quantum or something, where with every qubit that I increase, the memory exponentially increases, right? And I have to fit everything in the memory in one shot. If that's not the case, then generally, like in case of astrophysics and all, we have seen that you can transfer some part, work on it, until that time the other data is getting ready to be transferred. And it utilizes the GPUs effectively. So it's not just about storing it, but to understand how much part is spent on communication versus the actual kernel.
So the diagram you made, right, that is for the CPU architecture, right, on the board. So what does it look like for
It will be the same for GPU also. Every time it is the same. The only thing is the capacity is different. That's the only difference. It will be the same. No matter which architecture it is, if you would have heard, it's called as von Neumann architectures. Von Neumann said that there is something called as memory, there is something called as ALU. What I showed you was a von Neumann. Every processor, except if it's a quantum computer, then it is different. Otherwise, everybody will follow this. Doesn't matter whether it is GPU or CPU, the quantity and the speed will change in GPU versus CPU.
Yeah, thanks.
Further questions?
You talked about the CPU in CPUs. If you have a different architecture, you have different speeds. Can you explain a little bit more on that? Like how?
So, which is the most power efficient architecture currently?
I don't.
All of us know that answer actually. It's in your pockets. ARM, ARM. It's in your mobile phones. The reason why ARM was chosen as the architecture was because ARM is very power efficient. Mobile phones, no matter how much good compute I give you, but if it is draining the battery like anything, then it's of no use for me. Correct? So the way it is built is that it is very power efficient. The way its instruction set is, the frequencies and all, whatever they create as an architecture is very power efficient. Right? It is part of the architecture. The one that you generally have in your desktops is generally x86 or x64 architecture, which is given by Intel and AMD. Right? So they created an architecture which runs very fast as such. So it depends on a lot of factors like what is the instruction set, what frequency it is running at, what can be the what's the cache levels, all of that defines the architecture speed and power efficiency and all of those things. Okay? So, but all of them follow the same principles. It's just the instruction set is different or the way you utilize it is different. Nowadays, ARM is very popular. If you see world's power efficient supercomputers, ARM is now one of them. NVIDIA's Grace is one of the most power efficient CPUs, which is used in supercomputing world, not in the mobile phones. So NVIDIA did have a chip called as Tegra in the mobile phones, but we moved on to using it for supercomputing where it needed the most performance.
Okay. So if there's no further questions, then we'll continue. Correct?
Yeah, I will continue for half an hour, after which I will hand
then
it over.
let's continue the thing.
I have more half an hour, right? You tell me to stop whenever you want to. Okay, so before going to the actual thing, so unfortunately, I don't know if I have a Python code with me, but it would have been, so maybe I can show a very quick. By the way, this is an example of Python code, just for your reference. So if you are in Python, you would do import numpy as np, and then you have a function. Here it is doing a linear algebra BLAS1 function called as axp, which does nothing. It multiplies a scalar to a vector and adds it to another vector. Okay, so your basic linear algebra BLAS1 function. So this is how, if you use numpy, it will utilize CPU and sequentially it will do the job. Maximum it will vectorize your code. Similarly, we have something called a Numba. Numba is a Python side of the world where if you see, you can just say @vectorize, and if you see your input type that you're giving is float, and your target architecture for which it needs to be JIT compiled is CUDA. So it will now do this operation in parallel on the GPU. Right? So just a very simple example of the Python side of the world. But and is the same going to be MATLAB also has, I don't know how many of you use MATLAB, but MATLAB also supports the same feature. Okay, so I'm going to start with the concepts of CUDA programming. So one thing we have to understand is NVIDIA created GPUs, and every architecture needs certain architecture. Everything has an architecture. I just gave an example of ARM. ARM is an architecture, which means it has some instruction set like add, load, how many resistors it can have and all. So similarly, NVIDIA's architecture is called as CUDA, Compute Unified Device Architecture. That's the architecture of NVIDIA GPUs. And for every architecture, you need to have some sort of a way to program it, right? So you have a programming way or approach to that. And that's what we are going to just see how to program on the GPUs. And I'll try to cover as many concepts, but the main thing that I wanted to highlight was again that 80-20 principle, which is you will start with the code which is sequential. You like in C code, you will start with main function, and then in between, if there is a loop, that you will transfer to the GPU. How do you transfer that data or the code to the GPU is something that I will cover in a bit, right? You don't run everything on GPUs. By the way, there is no system which has just GPU. It has to have a CPU because GPUs cannot run an operating system. Okay, as simple as that. So you need to have a CPU as well, and everything starts with a CPU. In between, you transfer the data to the GPU. So I will just explain some of the concepts to you, after which they will take over to show you some hands-on programming. Don't worry, even if it is C code or Fortran code, doesn't matter. The concept that you'll apply in Python will be the same. So parallel portion of application. So the part of the code or the function that runs on the GPU is called as a kernel. Just some words, nothing more than that. Main concept is that a function that runs on a GPU is called as a CUDA kernel. And every CUDA kernel runs with multiple threads. So every thread will run the same function, right? But for different data. For example, if there is a loop, as I told you for this thing, and we'll see that example in a bit, right? And those threads which run on the GPUs are called as CUDA threads. A function which runs on the GPU is called as CUDA kernel, and and that kernel runs this function by multiple threads in parallel on the GPU cores. And the thread are called as CUDA threads, and you can practically run tens or thousands of threads on the GPU. Okay, because GPUs can actually handle a lot many threads. And why is that? I'm not going into the operating system concept because it requires more time to explain those things. So as I showed you here, a kernel is a function that is executed on the GPU. And as you can see here, for example, this is your data. right? So suppose this is an array on which you want to operate. There are, suppose, these many threads that you have launched, and every thread is going to run the same code or the same function. The only difference is, based on the thread ID, it is going to choose different data. Okay, and this kind of a programming model is generally referred to as SIMD, single instruction multiple data, which means you are executing the same instruction but on different data points. Is that clear? So the same function running, but based on the thread ID attached to it, you are going to work on different data based on that. Okay. But it is slightly complicated in terms of GPUs, and I will try to explain it. And don't worry, even if it doesn't get you are able to grasp it in one shot. It's sometimes very difficult, even for computer engineers. But after this session, you can go back. We'll be giving you more examples where you can go and study. So as I told you, a CUDA kernel runs as multiple threads. But in the GPU world, it's just not about multiple threads. You actually group those threads into something called as blocks. Okay, so you don't run a CUDA kernel as threads. You run a CUDA kernel as multiple blocks, every block having multiple threads. So it's not like you just launch 10,000 of threads. For example, here you are saying, I'm going to launch a CUDA kernel with 3 blocks, each having 8 threads. So the total number of threads that I have launched is 24. But I divided it into 2 levels of parallelism, which is blocks and threads. Okay, so this is part of the CUDA programming model. The CUDA programming model kind of mandates this kind of a hierarchy, and there was a reason why it was designed like that, because, and I will cover that part in a bit, why we added this problem. And that's why in the beginning, when CUDA was born, many of the scientists found it difficult to write codes because it required them to get this hierarchical parallelism. And this whole blocks run as a CUDA kernel, also referred to as a grid. Okay, so CUDA kernel or grid is the same, but I hope this goes into. So a CUDA kernel runs as multiple blocks, each blocks having multiple threads. There is a 2 level of hierarchy which happens, and this runs obviously on a GPU, right? So for which you need to understand the reason behind it, or how the GPU architecture actually is built. This is slightly going into the GPU. By the way, whatever concept I tell you is also true for CPU. If you don't know about the CPU architecture, the sequential code is the same which happens. So in case of a GPU, the GPU consists of something which is called as SMs, sometimes referred to as streaming multiprocessors. Okay, I'm talking about the actual hardware here. So a GPU consists of something called as multiple SMs, and every SM having multiple cores. So this is called as SM, and these are called as core. Okay, and you will have multiple like this. This is actually how the hardware of the GPU is. So it has something called as a SM, and inside SM you have multiple cores. On the CPU side, have you heard of things like this? Sorry, cores and... So in CPU also, you do have this concept actually. You do have CPU cores, but what are this? Sockets. These are called as sockets. So actually, when you write your code, it actually has the same concept. If you have not cared about it so far, there might be a high chance that your code might not be running efficiently, because they have their own cache. Then there is a common cache. So it is kind of a slightly complicated architecture, but forget about it. What I'm trying to tell you is, like GPU, CPU also has the same thing. So I'm not trying to debate on that part, but what I'm trying to tell you is, on the GPU, you have multiple SMs, and every SM has a core. So now, if you look at the diagram which I'm showing there, I'm trying to map the hardware to the software. Yeah. So it will have a common cache here, but the memory will be the same, RAM. It is always the same in either case. Whatever you allocate is always available to all of them, always. Okay, so the reason I am showing you this is to match the reason why CUDA became really popular programming model is because it was able to match the hardware with the software to get the best performance out of it. So a CUDA thread runs on a CUDA core. A CUDA block runs on a CUDA SM. That's the whole concept of two level of hierarchy, which means a thread is going to run on a core. So here, for example, it has 9 cores and 9 into 3. That many threads I'm going to launch in total. But every thread is going to run here like this. And this is going to be the block. So one block, 9 threads will run here. Another block, the 9 threads will run here. That's how the division behind the scene happens. Can anybody guess why? And the whole thing runs on the GPU finally. The CUDA kernel runs on all the SMs. Can anybody guess why we need this hierarchy? I could just run everything in every thread, right? Just run multiple threads. Sorry? No, that is bad for GPU, right? I already told you. Multiple functions actually means that you're doing multitasking kind of a job, not SIMD jobs. Distribution of memory to some extent, yeah. But let me cover the concept first. So in the CUDA programming model, when the CUDA was born, have any of you written any parallel code so far? Do you know what, do you always write in parallel, or do you have to sometimes in between synchronize and share data and do things? What is that concept called as? How do you make sure that every thread is able to get the consistent data? Do you take locks and things like this? What is this concept called as? Sorry? Communication between threads. So if you do things in parallel, a very simple example I will give you. So have you heard of something called as reduction operation? Basically, this is why I say that parallel thinking is very different from parallel model or parallel model. So suppose I wanted to add all of this to one single entity. So if I write a for loop which is sequential, how many operations am I doing? N elements, N operations, it will take N cycles to execute. If I were to do it in parallel, can I do it in multiple threads? Can I? How do I do this? This is how you do multiple parallel reduction operation. So you reduce the number of steps from N to log N. That's how you do, right? What I'm trying to tell you here is, can I write to the memory directly when multiple threads are doing this operation? You have to make sure that every thread is working on its independent memory. They're not writing to the same memory. If everybody writes to the same memory, then what will happen? Somebody can overwrite my previous data inconsistency, and all those data races and all those problems can come. But as part of CUDA programming model, we said that one block cannot share data with another block. It's not possible to do this operation across multiple blocks. So I cannot guarantee that I cannot synchronize or put a lock in a way that if this guy is working, I cannot make sure that this guy is not going to touch this guy's data. I cannot do that at all. So we made a condition that only the threads within the block can talk to each other, can communicate with each other, can lock and do any kinds of operation. They cannot do it with another block's threads. Okay, if you want to do those kinds of operations, you have to fix it only to this, within this. So here the threads can talk to each other inside, here the threads can talk, but across this you cannot do those kinds of logs or data arrays kind of a thing. Can anybody tell what could be the reason why to have this kind of a problem created for developers? It's a very simple reason. It's called as scalability. So today you have a hardware, we have a hardware on even on your normal workstations, okay? And that workstation can have 2 SMs with certain number of cores, okay? So if you see on the top, my workload requires 12 blocks, each having 8 threads. I have 2 SMs. So the amount of time it will take for running this is how many? These many cycles, correct? Is it understood? Because I have 2 SMs and I have 12 blocks, it is going to take 6 cycles to finish those workload, correct? Tomorrow I launch a better GPU. It has more number of SMs. So how many cycles now it will take? There was one question which was asked, if I take a new hardware, will it scale? Will it run faster? And this is the reason for it. What if I made a condition that one block, which is the 10th block, is dependent on 5th block, or 5th block is dependent on 6th block? Can I do this? Think about from an algorithmic perspective, you can get into something called a deadlocks. One is waiting for the other to finish, second is waiting for the first to finish, and you may never come out of it. So if you add dependencies, so it's called a dependencies are the evil of, is the root of all evil in programming, parallel programming. The more dependencies you have, the more problem you are creating. Because if you're dependent on each other, you have this problem of data arrays, deadlocks, this, that, and everything, right? So CUDA programming model inherently said that I am going to make my blocks independent so that in the future, if I give you a stronger GPUs with more SMs, your program will scale. Almost linearly it will scale. If I go from 2 to 4 SMs, it should double. It should reduce your time by half. That was the reason why GPUs kept on giving better and better speedups as the new hardware came. Your same code, once you wrote it in CUDA, could scale better and better and better with the newer hardware. That was one of the reasons why this additional overhead was given onto the developers. It was a conscious decision which was made. So tomorrow, you might even have a hardware where you have more number of SMs, a very powerful GPU, and some of the SMs might be even idle and you can finish it in one clock cycle. Okay? Is it clear? Is the concept clear, right? The part is not about writing it, but the part is to understand this concept. And now the free GPUs, which the free SMs, the question that you had, now I can run some other functions there. If I have free cycles, why not? I can give it other work. So it is all about scalability. Yeah. It has never changed. From the day one when GPUs were born, it has remained. That's one thing about GPU architecture. Nothing has changed from day one. From 2007 is the same concept which continues. We have given some relaxation on some communication patterns, and all, but the concept still remains the same. It's the same course, SMs. You will generally see GPU configuration like how many SM it has, how many cores every SM has. It will always, and your program that you have written in 2007 will work exactly on the newer generation also, and it will scale. How do you define the optimal number of cores as a hardware engineer? So that I will have to ask to the hardware team, but generally it's a multiple of 32.
So what stops us like making more and more SMs with lesser and lesser cores?
There are a lot of problems. If you understand the semiconductor industry, the world is not about performance anymore. The world is about performance per watt, power. So the power it requires, the more power it requires, what will get generated more? Heat. It will actually melt. It can melt. So you require that kind of a cooling system. So there are more challenges in the semiconductor industry. That's a different topic. But you can't keep on just increasing the number of SMs exponentially. So you will then have the maximum number in one GPU. Then I showed you that you can have multiple GPUs, and then you go across nodes. That's how you will scale.
Thanks.
Okay, so I just explained all of this concept. So a kernel executes as a grid of thread blocks. Every block has a group of threads, and within the block, the threads can communicate with each other or have these locks and things like this. Synchronization can be done using something called as a shared memory. The shared memory is per SM that I was talking to you about. Per SM, there is one memory called a shared memory, which can help you to do those kinds of synchronization within that block, not across the blocks. Okay, so every kernel will obviously, now you can have a one-dimensional grid block, you can have two-dimensional grid block. Suppose if you have an image is two-dimension. Similarly, you can have three-dimensional grid block for across time. So you can launch 1D, 2D, 3D based on how your domain is. You can launch different types of configurations. So you will always have a thread ID and block ID attached to it like .x, .y, and .z. So it will always have an ID in X dimension, Y dimension, and Z dimension. So it's up to you whether you want to launch in 1 dimension, 2 dimension, or 3 dimension. Is it clear? So let me skip this part because it might not be required. So is this something that you are covering, Akash? The CUDA part? Okay, but you will be covering the thread ID, block ID and all, right? So I can, okay. So we have a break in 5 minutes, so I don't want to start the new topic. But is there any question for me from a concept of this understanding? Yeah.
Clock rates are slower.
Yes.
Sorry, what is the typical clocks they reach, and what is the roadmap?
It changes from one to the other. For example, your latest CPU can have 3 gigahertz, 4 gigahertz frequency, while GPUs max out at around 1 gigahertz. So they're generally 3 to 4 times slower as compared to the CPU cores.
So when you mention 1 gigahertz, threads can run at 1 gigahertz clock?
So threads is a software concept.
Yeah.
What I'm saying, gigahertz is a hardware.
The core.
Sorry? Yes, that's the gigahertz, yes.
One more related question. When you mention lightweight thread, could you define what makes it called lightweight or high?
Okay, I will have to go into operating system concept. If I'll explain it, but for people who are not able to understand, you can skip, as in ignore it if you want. But is there any other question? Yeah.
16 physical cores. But then because of hyper threading, they say you have 24 or 32 cores. So how does this threading work? What is it different from process, like a number of physical processors, and how does it like increase when you do threading?
So hyper-threading is, okay. So this chair is there. How many people can sit on this chair? At a time, it's a hardware concept, right? So if you have one core, only one thread will be running at a time. What does hyper-threading mean is, in case that thread is waiting for something, like data to come to it or something, you can switch to the other thread. As simple as in, I'm just telling it, simplifying it to that bit. But that's what it gives indirectly. Because, but at a time, you have limited hardware. So only one thread can run at a time and utilize it. For example, one thread can utilize the integer units, while the other thread can utilize the floating point units. So it depends on the resources of that. But that's the concept indirectly. If the resource is available, yes. If the resource is not available, then only one can sit.
Thanks.
Hello. Yeah. So when you were talking about thread IDs, so what is the logic behind that? So there's X, Y, and Z. So if I say like X and Y are like cores maybe. So
So you don't need to go to that level. You don't need to work.
What is the Z?
So that is more of your domain concept. How do you want to divide your work? Which is, if it's an image, you would ideally like to give like X, Y coordinates, right? So you're dividing your work. How does it behind the scene relate to the course?
So it's not a physical thing.
No, it's not a physical thing. It will and it will change from one architecture to the other based on what we saw it being used the best. So you can ignore what it is behind the scene. You cannot map it exactly like, oh, this is going to be like this is going to be like this. So you can ignore that part. It's more from your thinking perspective. Okay, so if there are no questions, there was a question on what do I mean by lightweight threads. Okay, so maybe let me start this with a question. What is a thread? What is a thread, right? Like we know core. What is a thread? Sorry? No. Core is hardware. Thread is software concept. So core is actual hardware where it will run. Thread is a software concept created in our operating system. It's a software. So if you were to write a software, how will I write a software? What does a thread need? What does a thread need to execute anything? So think, so some of you are not familiar, but think of a data structure called as thread inside, behind the scene. And what all things it requires to execute anything? Yeah, memory. So there are different types of memory, but yes, it does require memory to execute. So suppose I wrote a program A equal to B plus C, K equal to I plus J, like this. So how do I know which instruction I am running? Which thread is executing which instruction? It's called as a program counter, which means it tells you which instruction I am supposed to run. So it will have something called as the location to that instruction. Okay. So it will have multiple things inside it to execute inside it. So is this concept clear? So thread is a software concept. Behind the scene, it is like a data structure which has things to execute, to do something about it, right? So what is there in the CPU thread versus GPU thread is, as I told you, the GPU thread, all the threads execute the same instruction. So it doesn't need to maintain a lot of things that the CPU thread actually require, because CPU threads do multitasking. They can execute this instruction. So like one thread can execute one function, other thread can execute another function, right? Or it can do different kinds of things. So the amount of data and the things that it requires is much, much, much more as compared to a GPU thread. That's why GPU threads are called as lightweight, which means they can be switched very easily. They can be context switched very easily. That's why they're called as lightweight. That's the higher level concept, I can say. 1.5 hour.
Bharat, hi. I just wanted to know, why is the GPU thread slower than a CPU thread?
Frequency.
Just because of the clock frequency, there's no
Clock
other reason.
frequency.
So then why was the clock frequency low for GPUs? Is there a particular reason?
If I increase the clock frequency, what will happen?
The power consumption will...
Power consumption will go high, heat dissipation will go high, it will become a furnace, it will melt. As simple. If I am giving more cores, I have to make it within a power budget. So I have to reduce the frequency. That's the concept.